Okay, thank you. Good afternoon, or good morning, I'm sorry. It seems like it's afternoon already. We'll wait for a few more people to come in as they come, but that's on them. My name's Chris Teaf. I'm a toxicologist at Florida State University at the Institute for Science and Public Affairs, and also the president of Hazardous Substance and Waste Management Research. I'll be your moderator today. I'll also speak, it's a mixed blessing. I want to first introduce the initial speaker, Dr. Ziqi. When I asked him how to pronounce his name, he said her, so I don't know if he's joking with us or not, but he or her. Zeke?
Thank you, Chris. Good morning, everyone. Yes, my name is Ziqi, but I got called, Ziqi all the way, so just call me Zeke. Today I'm going to continue my last year's talk regarding PFAS toxicity and the federal and the state dynamic regulation. Let us start with the history of PFAS. I'm not going to talk what is or what are PFAS. I'm going to start with a molecular structure on the top left corner, which is Teflon, polytetrafluoroethane. This product was invented by one of my Ohio State alumni when he was only 28 years old. Got his Ph.D. 2 years later in 1938. He was doing some research, tried to create a new freon product, chlorofluoroethane. However, accidentally, he found out a hard, solid material, which did not resolve in water, oil, solvent, acid, base, elevated temperature. That triggered our next 70 years good product. As you can see from 1940 till today, PFAS product material have been used or applied in our industry, daily life, household product. Second point I would like to point out is the two dominant manufacturing process, ECF, electrochemical fluorination, which was operated by 3M primarily before year 2000. This process generates, I can't use the little, as you can see at the right bottom, both even and odd carbon chain PFAS group, which also contains roughly about 30% branched isomers for each PFAS compound. In contrast, the other manufacturer process, fluorotelomerization, which mostly dominating the production after year 2000, which only generate even carbon chain and linear PFAS compounds. So these two manufacturer process, I'm going to touch them in a moment regarding chemical fingerprinting analysis. A third point I would like to emphasize here, in early 2000 or 2010, the US phased out long-chain PFAS, primarily PFOA and PFOS production or use. However, it's important to note that the manufacturer or production of these long-chain PFAS compounds are still in process, just not in US. So the total annual production amount quite similar to US pre-2000. So even we know they are not here, but have some way to be here, like your computer, electronics, the car, O-ring, vital material, which are made from PFAS. This chart shows the PFAS group or classification or family. We all talking about or heard of up to 10,000 compounds with 4,700 with chemical registration. However, our focus pretty much on the left side group, perfluorinated alkane substances, or the subgroup of PFAA, the primary group or early attention for drinking water analytical method. The middle group is the polyfluoroalkane substances, which are in large quantity in production. This group of compounds pretty much are the precursor or intermediate for the final product. In the field, particularly landfill, they can be converted or transformed into the left column, which is called forever chemical or terminal chemical, which will not degrade under natural conditions. The most right column is the polymer column, which are the solid material we are using in our life, mostly for heat resistance, water resistance product. This group are considered with less or lowest toxicity. So many states starting to set standard or criteria for the left column PFAS compounds, primarily PFOA and PFOS. So I'm going to introduce how the toxicity value are developed. As you can see from the curve, in the laboratory or study, scientists feed the target subjects with a sequential concentration of a chemical, not only PFAS, any chemicals. Then they observe the response of the subject, a rat or monkey or human being, to the health effect. So it's kind of our scientists have a SOP or standard procedure to follow. Are this group at 10 ppt happy? At 20 ppt, they losing their appetite. 30 ppt, they kind of, losing body weight. From there, they decide a point of departure or toxicity endpoint. Okay, 10 ppts. However, those data those laboratory studies are based on, some animal study. From there to transfer to our human being, there is a large number of uncertainty factor, could be up to 3,000. So we get 70 ppt health advisory level. Is this safe? Last year, we got a question. What's the big deal? Will we drop dead if we drink 70 ppt water with PFOA or PFOS? No. Just like cigarette, one cigarette, one pack, or one carton, it won't going to kill you. And people smoke daily could live to up to 100 years old. However, the science can tell the group of people smoking will have more chance to get cancer than non-smokers. That is the chronic long-term toxicity for most of our environmental treatment remediation process. As you can see, there are multiple adverse health effects for study to determine our final reference of those. Let's start from 2009, the EPA Provisional Health Advisory for PFOA and PFOS. At that time, EPA used rat data for PFOA and monkey study result for PFOS, then applied the uncertainty factor, calculated the child risk level with a 20% source contribution, assume 20% intake of PFAS from our drinking water. At that time, the health advisory level were 400 for PFOA and 200 for PFOS. Many company or stakeholders at that time, were triggered the proactively to sample their site, at selected well, treatment effluent. Oh, we are good. We're at 280, below the standard. However, only a few years later, EPA updated the toxicity data or evaluation process. Now the lifetime or final health advisory are 70. What do? We all know 5 years ago, big report, news, everything about PFAS. Over the last 5 years, you go to any conference, 50 to 70 topics are PFAS related. So, is this 70 the end? No. Many states, particularly Northeast states, they set their standard. Although the laboratory study similar reference, however, they applied different data screening or processing process. Then they get their own value. It can be 10 times lower, 10 times higher. As you can see, Massachusetts state, same data set as the EPA. However, their uncertainty factor is 3 times lower. That's because their MCL is 20 ppt. From this map, you can see all the chaos from federal, state regulation, drinking water, surface water, groundwater, action level, screening level, notification level. Please note these are rapidly changing. An example here I would like to point out is state of Maine. 2 years ago, their criteria was 400 for both compounds because they applied the same approach as the EPA process. However, without that 20% relative source contribution factor. Then last year, they dominated the PPT 70 as groundwater standard. For drinking water, their standard now is 20 actually. So EPA started to develop or process the MCL for drinking water. We heard a lot this morning. It's based on science or awareness, public pressure, or public comments. No matter what, these two compounds are the first two chemicals over the last 25 years, which, making the final step. EPA is going to establish MCL. All other emerging contaminants we heard or we have been remediation, 1,4-dioxane, perchlorate, 1,2,3-chloropropane, so many other chemicals. They are still in their emerging phase, but for PFOA and PFOS, they are in the final step for drinking water enforceable standard development. EPA Science Advisory Board, they reevaluate or evaluated the new data after 2016 health advisory, mostly the publication between 2013 and 2021. Several hundreds of toxicity studies. They nailed down to about 100 publications with data usability and high scientific defensive data. As we can see, compared to 2016, now the toxicity value are 10,000 times lower. That literally means the MCL goal will be 0. How high or what value will be set for MCL, that will really depend on, technology, cost, analytical method. Right now, most of our available analytical method at about 1 ppt level. So it's not possible or going to be likely for MCL at 0.0001 ppts. Not at the MCL development. We heard this morning, EPA already developed the final toxicity data for PFBS and GNX. These two compounds were considered the replacement for PFOA and PFOS. Okay, they should be less toxic or even not toxic. However, you can see their toxicity value quite similar to 2016 PFOA, PFOS level, or even lower. You can see GNX now, the health-based value should be around 10. State of North Carolina set the MCL, they are the first state set MCL at 140. That's back to 2017. Today, will they revise the MCL? Will they need to treat their river water, to a low standard? At least state of Ohio started. Their MCL or action level for GNX now is 21 ppt. I'm not going to repeat this diagram from Tyrone, but would like to highlight, the MCL deal is coming in year, or can be postponed, but very likely will be there, just which value. As long as that value is set, then we will have our IDW potentially be characteristic hazardous waste. Even circular record don't set these two compounds as hazardous substances. A second point, I want to re-emphasize there are more coming with toxicity value. Although we understand if you have done enough assessment, primarily will be PFOA, PFOS, as the highest, most detected compound at most of our facility. However, some facility we do have elevated PFBS, PFHS, PFHA concentration, if we're going to set them at 20 ppt. So all this rapidly changing toxicity value and federal state own setting standard affect our decision making, highly challenging situation for stakeholder. What should we do? Let's start with impacted drinking water data. This morning we heard, Colorado, Michigan, few states, they did statewide drinking water survey, not many really exceeding 70 health advisory level or their state action level. I just want to repeat the UCMR 2013-2015 data, which already indicate over 6 million residents with drinking water impacted at 70 ppt. Almost there. Please note, at that time, the reporting limit was about 20 to 40 ppt-ish. We know already Northeast few states, their standard today is 8, 9, 12, 15, 20. We are doing some small system modification now for the local small system community. Try to remove that 15, 20 PFOA, PFOS level at this time. Then after 5 years, the UCMR 5, there will be 25 PFAS compounds data coming out. At that time, the drinking water standard could be 10 or 20, and there will be many more PFAS compounds with toxicity value available. Another uncertainty is for our environmental business. What are we chasing? In Florida, we use 70. The footprint of impact can be that red color, red contour area. If we are in Northeast, we go way beyond all the boundary wells, not enough. More wells will be needed. You could end up with urban anthropogenic background. For treatment, if we're treating at 70 ppt and 10 ppt, there will be 5 to 10 times the cost difference. If we're treating long chain and compared to short chain, that can be 100 or 1,000 times cost difference. I'm not going to repeat the EPA guidance for destruction or disposal through landfill, deep well injection, thermal treatment. However, the DOD facility just had a memo coming out last week that no more incineration at this moment until we have enough research science data to indicating, burning is a good or defense way with disposal. Maybe we can hold the waste like EPA recommended. But if you have other TCE or vinyl chloride characterize the waste as hazardous waste, then you got to dispose them. Then why thermal or incineration is a concern? I borrowed this slide from New Hampshire. It's a plastic facility. Their chimney migrated or airborne deposited PFAS plume to the groundwater over 50 square miles. However, you can see there are many small dots here, there, localized contributors. You cannot, blame the facility for every PFAS molecules. There are some forensic or chemical fingerprinting tools available. I'm not going to read through, like isomer during manufacturer processing, top assay analysis, or high-resolution mass spectrometer, which can be applied to tell, 2 different sources or 3 different sources. The primary factor will be our professional judgment. Really, are these 2 different plumes? Are they same plume from same facility, upgradient or downgradient? How about the PFAS homolog, their migration or fate transport difference causing the distribution pattern changes? So my coworker, Nick Barnes, tomorrow will have a presentation, talk more detail about our conceptual site model approach for site assessment. I'm going to end here. The main message I would like to deliver is we know more and more PFAS are coming to attention, just as PFOA and PFOS. their science development are changing daily, monthly, and the regulation will follow the science. So that means they will change. That cause our business or stakeholder really decision-making is not easy. Then what is the end? What is our next step? Just like Florida or EPA, that will be up to the regulator, just in the opening session, they have a discussion from the Florida state perspective and the EPA perspective. That's my talk for today. Thank you.
Thank you. Okay, I think we'll probably follow the paradigm that was earlier today, which is hold the questions until the end, if you don't mind. My name's Chris Teaf. I think that's about the third time I've heard the perfect characterization of PFOS, which is like Florida weather. If you don't like it, wait about an hour. There's more and more and more information becoming available very, very rapidly, and I would encourage you to make some contacts here with folks in different fields. It's impossible to keep up with it. Keeping up with the toxicology part of it's terrible. The engineering part's terrible. The geology part's terrible. The analytical part's terrible. So find a team of folks that you can bring together for a particular site or sites. This point hasn't been made, oddly, although it's been obvious, I think, to me that you're dealing with what we call PFOS. It's certainly thousands, maybe even tens of thousands of substances for which we arguably know enough to deal even remotely with a couple of hundred. More and more information is becoming available. A lot of money is being spent to gather information on the toxicology and the fate and transport, but we're a long ways from where we need to be. This is if you happened to be asleep for the last 10 years, this is a summary of where we are with PFAs. The strongest chemical bond, chlorine and fluorine, carbon and fluorine. The chain lengths are going to define the effects, both in terms of fate and transport and in terms of toxicology. Yeah, it's true that PFOA and PFOS are the most studied to date, but that's changing, as you just saw. And we're beginning to realize that maybe some of the things that we thought we would next focus on, the Gen X compounds, for example, hexafluoropropylene oxide, may or may not be better. We'll see. We'll see where that ends up for us. These are the important properties. Most of the folks that are here because you know this much, why they were used and what their benefits were and what their detriments are to some extent. The issue of mobility at first caught our attention for groundwater, but it's also clear that it has some dietary applications. The linkage between air and water and soil transport are becoming clear to us as far as their importance, but they're not really all that clear to us yet with respect to which things to focus our attention on, and it may differ with the site. And finally, in addition to having explicit toxicological effects one by one and on an acute basis and a chronic basis, they're bioaccumulative. And so we may find that what we assumed to be true in the short term is actually true to even a greater extent over time if we don't control the exposures of various types. Again, many of you know these things. I thought that everybody in the first session handled it well in the sense that a lot of ground was covered multiple times because people came not knowing necessarily what the audience was going to be. But it's clear that these things are far more prevalent and pervasive than we maybe realized 10 years ago. All of these things have been talked about. All these potential sources and environmental vectors have been talked about. Really, really important. The most recent one, of course, is food packaging that's getting our attention. And that, as John Gardella said earlier today, has not only implications for our dietary exposures, but also for waste management decision-making. So they really are truly penetrating essentially every aspect of waste management and toxicology and engineering. I'm not going to touch on the analytical issues at all, other than to note that, interestingly enough, while I am interested in the toxicology and the establishment of protective levels, in all likelihood, at the end of the day, at least for the next decade or more, we're going to be dealing with detection limits as our criteria, because we simply don't have the ability to identify target organs or specific toxicological effects that are sufficiently protective, because we keep going lower and lower and lower. Parts per trillion, I mean, we're going to be in parts per quadrillion soon, and it's the very rare substance or substances for which we've ever had to deal with those kinds of situations where we really can't tell you right now what the appropriate protective levels are. Every time we get a new study, those numbers drop. So the analytical issues are incredibly important, because they will almost certainly dominate the decisions that are made in the next 10 to 15 years. I love this slide, by the way. Where aren't they? When we say where are they, but where aren't they? Arctic, Antarctic, bottled water, drinking water, vegetation, food supply, bottom of the ocean, Mount Everest, the summit of Mount Everest. So if you sample a site or a location and you're including PFAs in your analytical profile and you don't find them, get a new lab. So they're everywhere. We have, the more we look, the more we find. And it is becoming it's both a problem and a really interesting set of circumstances. The similarities for these substances, you heard some of from Dr. Hare, and there are more dissimilarities than there are similarities. We tended at the outset to want these to be sort of circumscribed, and maybe we had a fairly good handle on the variability. Negative, negative. We can use that information to a certain extent in structure-activity relationships for toxicology, but we're learning quickly that those have their limitations. And it turns out that probably the diversity is going to be the rule rather than the similarities. And that isn't really true. We've dealt with relatively simplified groups of compounds. The chlorinated solvents we thought were hideously complicated. No, not really. Not really. We thought the metals were probably the kind of thing we could get our arms around with respect to similarities in effects. Yeah, probably not. And these dwarf that in complication and specificity. General statements are difficult. The structure-activity relationships are okay, and we can use them a little bit, but the farther down we go and the farther we go in the toxicological evaluations in the literature, the more we realize that we're limited more by our ability to measure endpoints than we are in our ability to measure variability in the kinds of effects these substances can cause. The animal-to-human extrapolation process that we've used in toxicology for 60 or 70 years is failing us a little bit here, because there's not only variability amongst species, animal species, but also differences between humans and animal species that we use as our toxicological surrogate measurements. Half-lives turn out to be really, really important. Our historical toxicological literature has done relatively short-term studies or chronic studies that are on the order of months to years. It may turn out that the half-lives of these things in the environment far outweigh our ability to predict what those effects may be down the road. And I'll give you an example in terms of human tissue concentrations in a moment, which we heard about this morning, and that was good. I'm going to give you a little bit more detail on that. A couple of different approaches have been used or proposed for toxicity assessment and evaluation of acceptable levels. Those are additivity, relative potency, and a related toxic equivalency endpoint approach. The last two are really two sides of the same coin, but what's happening is we're understanding that the endpoints that we measure in animal studies or that we try to assess in human studies don't always lend themselves to these kinds of aggregate additive or synergistic relationships. And I guess I should stop and say, I don't think there's any evidence yet, to my knowledge, about synergistic relationships amongst the PFAs, but that may be because we're not very far along in our ability to assess those particular kinds of effects, synergistic effects. People say synergism, and what they really mean is additivity for the most part. Except toxicologists, we mean something different than that. The ongoing federal and state studies that have been conducted are continuing to address these knowledge gaps that we have. I mean, we all recognize what they are, but the difficulty often is constructing the experiments and constructing the kinds of analyses to get the answers that we don't have. And it's partly a function of the number of substances, and it's partly a measure of the inflexibility or inaccuracy or lack of ability to detect different kinds of changes in the endpoints that we have. So I don't think that's going to change anytime soon unless it becomes possible to assess things by more specifically biochemical measures. Right now, the kill 'em and count 'em doesn't work anymore. Exposure determinations. We tend to look at exposure determinations from our own perspective. If we do fate and transport, we're looking at groundwater or soil or air exposure. If we are in the public health field, we often look at groundwater or drinking water or the food supply. But it's in all likelihood, if you measure human serum now in any group of people, you're measuring all of these things. You're measuring all of those potential exposure points, and it's very difficult, probably impossible at this point, to establish for any individual, other than to say it's probably a function of all three of these four components. Which component is greater? You would need to know something very much about their drinking water consumption, their diet, their occupation, all the kinds of things we acknowledge conceptually are contributing to an overall dose in a human, but we have a very difficult time determining which one is more important for any particular individual or group of people. And as you've heard hundreds of times probably already today, the science is still emerging. Again, if you don't like it, wait about a week. There'll be 100 new publications. So the FDA testing is kind of interesting to me because this is one of those ones where we thought we had a pretty good handle on it for some substances. Dietary exposure, going back to about 2012 for the PFAs, is reasonably good. It's improving, and I'll show you a slide in just a moment about what we do know about it. There are now 9 PFAs in testing protocols with FDA. 5 of them you're pretty familiar with, the PFOA, PFOS, PFNA, hexafluorosulfonic, and PFBS. There are also 4 more, which have much more lengthy and complicated names. I brought a list with me of these 9, and actually out to about 12 carbons. If anybody wants one of them, I've got the abbreviations and the actual name if you want to have one for your scrapbook. They assess dietary contributions from dairy, produce, meats, and grains. And they ultimately concluded at the outset in 2012 that there wasn't a human health concern for those initial 5. They're continuing to look. Those data are coming in. They take a long time to generate through the FDA and through CDC. So here's human serum data dating from 2011, 2012 measurements to the present. Well, the present as far as they're concerned, which is 2017, 18. And you can see that they've dropped by about 30%. That's probably a function of recognition. It's also probably a function of identifying those most likely sources in the diet, but it doesn't necessarily limit itself to diet. These are also going to have contributions from airborne exposure to the extent you have any, or drinking water exposure to the extent you have some, either through bottled supplies or municipal water supplies or groundwater supplies. So this is a measurement reflecting anyone, mine, yours, total exposure, and what our serum levels are. This is for PFOA as the blue, considerably lower levels, and for PFOS, which is the orange, considerably higher, but if you look at the reduction over time, it's roughly the same. It's about 35%. Now, in terms of the toxicology, we look at two things in a broad sense, the cancer and the non-cancer. From a non-cancer standpoint, as you heard from Dr. He, immune response, in some cases delayed skeletal ossification is one of the endpoints that's used to extrapolate to protective levels. That, in fact, for PFOA is the basis for the reference dose, the non-cancer reference dose from EPA. They also measure a variety of things that we can tell you have changed with exposure, but we don't always know what they mean. But that, in fact, is sometimes the way in which the criteria are established. If we see biochemical changes that are judged by some measure to be of health significance, we use that as the criterion. Delayed mammary gland development is one that's observed but not fully understood, but has been used in the establishment of default criteria by some states. Reduced fetal growth is another, separate and apart from the reduced fetal ossification, the speed with which the bone density increases in a fetus. And we're always extrapolating from high-dose animal studies over longer periods of time to human studies. It's the best tool that we have at the moment, aside from biochemical measurements, as we get better sense for what the biochemical measurements mean and how we can relate those to actual adverse physiological effects. We're going to have to use those as additional information, supplementary information. And then finally, I haven't heard anybody say this, but it's really, really important that we be able to somehow establish the difference between association and causation. So we can oftentimes see two things varying in concert with one another or opposite from one another, and we get a sense for the fact that one is related to the other. But we don't always know, and it's much more difficult to tell whether causation is the reason for that or whether they're just varying, again, in the same direction or in different directions. So separating causation from association is a tough one, and it's one that tends to be glossed over sometimes. We tend to use things that vary in a similar way as bases, and we probably haven't always been right about that. With respect to cancer, let me say at the outset that for most substances we've ever dealt with, the non-carcinogenic effects are less restrictive when used for the basis of criteria than the carcinogenic effects. It's almost always the cancer potency or the cancer endpoint that drives the cleanup criteria or the health-based criteria. It looks like that may not be true in the case of the PFAs. And maybe it's going to be true for some of them and not true for others. But it's going to be very interesting because, again, we're going to be driven by detection limits for some time now. We'd like to say we're doing things for the right reasons, and we might be, but we won't know for a while whether that's true. And that is what is the basis for the really tight and increasingly tight regulatory approaches to these substances, because we don't know. We wish we did, but we don't. Someone mentioned earlier, and I think maybe it was John, although I can't remember, that EPA's cancer designation for these substances is changing, and it probably is. In 2006, it was called likely. This is for PFOA anyway. It's now much more likely to be identified as suggestive, and I don't know where we're going to end up with that. But again, what difference does it make when the non-cancer-based criterion is so restricted that you can't even detect it? It doesn't matter which endpoint you're using, cancer or non-cancer at this point, because the either number is going to be lower than the detection limit. A couple of things that have been happening recently. A number of speakers have brought you up to date on the kinds of things that they're dealing with on a regular basis, literally changing by months and weeks and days. Going back to the middle of 2021, there was a PFAS. It was sort of industry, but it was sort of consultants, and there were some regulatory personnel as well. And it got some pretty broad attention. The first one was in May of 2019. The second one was in July of 2021. And if you're interested, this publication by Zudro is a really good one. It explains in detail the things that were considered and the conclusions that were drawn by this group of experts. Their goal was to share knowledge amongst these experts, all of whom do different things: kidney folks, liver folks, cancer folks, neurological folks. And they considered different exposure assumptions in these toxicological evaluations. They concluded that there are substantial differences of opinion regarding critical effects of PFAS, how to consistently interpret and apply that information for setting toxicity criteria. So this is, arguably, this is the group of people who know more about this than anyone else in the world. And they concluded that, yeah, we're not there yet. Again, that doesn't mean you can't do anything, but it means that you are going to be constrained by, in many instances, going with the most conservative view of something until more is known. They said that a class-based approach is a long way off. That's probably true. Doesn't mean, again, that it's not possible to do that for some substances, but it may be that it's going to be very difficult to do that for the group as a whole. And one of the things that was mentioned, I think I have this on the next slide. Yep. Phil Goodrum, who's a good friend of mine and who I know very well, concluded that it probably, if you're going to do a class-based approach at this stage, the best you're going to be able to do is to separate the sulfonic acids from the carboxylic acids, at least chemically. And so that's something to think about if you're in the health field. We may not be able to aggregate all PFAs, but we may be able to aggregate some. Not sure if anybody here is involved in this, but there's a study going on now that was started last year, but now there's a health consultation that was released about 3 months ago with respect to a Peace Air Force Base study up in New Hampshire. Really good piece of work. It's continuing. They just closed another enrollment grouping in December of 2021, 5-6 months ago. And they'll be looking at this group of individuals as separate theoretical or potential exposure categories. Adults that worked at the base or studied at the base in training of some sort or another. Children that were in daycare at the facility. Children that were born or breastfed by an eligible mother. Adults in that town in Newington, New Hampshire with wells, drinking water wells from 2004 forward, and then non-exposed controls. This is going to be a really good study, and I think they've thought it out in advance and addressed some of the kinds of things that we often wish we would have addressed in longitudinal studies like this, looking at PFOA, PFOS in blood and urine, and it looks like they will eventually want to do at least 7 more studies in 7 additional states of a similar type. Probably at Air Force bases, that's where they seem to be headed in this piece of work. A little bit of recent research and guidance. If anybody, don't write this down. If anybody wants this, let me know. I'll send you the slide. This is a primer on the most recent kind of information that's out there that you might want to get a hold of if you care, if you're not a geologist or an engineer. But these are really good pieces of work, and they represent the kind of thinking that has taken advantage of what we know to this point and built it into research that moves the ball forward. Some examples of existing regulations you heard earlier today. There is no MCL for PFAs. It's allegedly in progress, and I say allegedly only because it could be a long time in coming. It's what I would say is that we're working on it. But I don't see, let me take that back. Because the MCL is not only a health-based number, but also includes cost and technical feasibility, it's possible. And that number could be established and then revisited on the schedule in the future. But right now, there is not one. You've heard many times earlier that the sum of the PFOA, PFOS is 70 for the time being. And I learned something this morning about some of the other states that seem to be taking even a more aggressive approach than that. Florida, of course, uses the 70 sum. California has adopted a couple of public health goals recently, set 0.007 nanograms per liter for PFHXS, hexafluorinated sulfonic acid, and an advisory of 2 nanograms per liter, for PFHXS, and the PFOA is 0.007. I mean, these numbers are functionally zero. They're useful in the sense that any number you compare to this is going to be greater than these, but it doesn't tell you a great deal about how close we are to the real answer, and that's a tough one. And I don't think it'll be, I mean, Jorge said we were going to retire on this. We might be dead before this gets resolved. Not of that, but dead. A couple of things you heard about from the EPA folks this morning about various actions that are going on. It's moving very quickly. The de minimis exemptions that I've learned about recently evidently are now no longer enforced. 100 parts per billion. Policy changes are moving fast, really quickly. Again, check tomorrow, check next week, check next month. They'll be different. The council was established in April of 2001. Has got a ton of work done. Like any other organization within a group like EPA, there were some growing pains, but they've really gotten a lot accomplished in the last year, a little over a year. The first toxic release inventory materials were released in the summer of 2021 for 170 substances. Coming up, some additional things. So April and August, a couple of documents came out which were toxicological evaluations of particular isomers. In October, the human health toxicity values for Gen X came out, and 2 record rulemaking efforts were initiated. The Science Advisory Board in 2021 was asked to review 4 draft scientific documents that have been put together by the agency. So things are really moving quickly. April of 2022, the draft report came out from the Science Advisory Board, and several people mentioned that literally today, tomorrow, and Friday, or tomorrow, Thursday and Friday, there are going to be meetings that are held for this very specific purpose. And that's the PFAS review panel. So certainly, PFAs have the potential to cause adverse health effects, no question about it. The question is dose and duration. We're not where we need to be in terms of knowing that. And that's true for people who say they're always a problem and people who say they're never a problem. And you can find them. There are people who will say both of those things. The difficulty relates to setting these acceptable levels despite large uncertainties. The way in which uncertainties have been handled in the past typically has been by just assuming that you're going to apply uncertainty factors or safety factors. But I think what we've learned with the PFAs is that it may be that you can't do that yet. We don't know what the uncertainty factors are. Increasingly aggressive approaches have been taken by agencies in a variety of states. EPA is extremely active in this area right now. Probably more so than any substance that I'm aware, or any group of substances I'm aware of, maybe beyond lead. Lead at one time received this kind of attention, but PFAs are really getting everybody's attention. There are massive assessment, characterization, and evaluation approaches underway. There's multi-district litigation going on. One of them is housed in South Carolina, but it involves a lot of people, including many in Florida. So those are the kinds of things to keep an eye on if you're a scientist or an engineer and you're asked to provide guidance to one or the other of the parties in those kinds of litigation. It's complicated. It's going to stay that way for a while. So with that, I'm going to stop. As I said, we'll wait till the end for questions, but please hold your questions, and I'm going to now turn it over to Chris Gurr to take us up towards the lunch hour. Thanks very much.
Okay. I'll start. Hello, everybody. I'm Chris Gurr with CDM Smith. I'm an environmental engineer, which means I use science and use tools to drive towards solutions here. And I think maybe my job is a little easier than these guys' jobs, but thank you so much for all your hard work on toxicology. Certainly a very complicated and difficult topic. I'm gonna talk more about the application, PFAS fingerprinting. I do a lot of conceptual site models and fate and transport, and certainly for everybody that does that, we've really been, pushed to understand this new class of compounds, which has very unique properties, and there's a whole diversity of it. It's really been, a difficult time, I think, in all of our careers, but an exciting time as well. I think we've seen a lot of the results of UCMR studies, paper from a few years ago, that talk about the broad, impacts across the nation. But in fact, I want to start really small here with one person. And, Zeke talked earlier, he talked about the 2009 provisional health advisory level, and then in 2016, we had a final HAL. And in the middle of that period was a really important event, which I think really moved the needle, and in my mind, we can draw a direct line from Hoosick Falls, New York, straight to where we are today discussing this topic. In 2013, Michael Hickey's, who lived in, and still does in Hoosick Falls, his father died of kidney cancer. And in his grief, Michael Hickey started to explore, were there external factors, some sort of exposure that his father had, that led to his early death. And Michael Hickey's father worked for decades in the St. Gobain Performance Plastics plant in Hoosick Falls, which is upstate New York. It's practically within spitting distance of Vermont, so definitely New England. So look, when Mr. Hickey looked more into the environment that his father was in, he learned that his father worked with this weird class of compounds that had a carbon and fluorine bond that was man-made and didn't occur in nature. And of course, that's PFAS. And Mr. Hickey got more and more concerned about himself and his neighbors, and took it upon himself to sample not just his well, but the potable supply wells of his town and of his neighbors, and of course found PFAS all over Hoosick Falls. He elevated this to his city council, and it eventually got to the governor's desk in New York. And in a historical context, this point in history in New York was right after the Flint water crisis. So New York State not wanting to repeat the government leadership errors that we saw in Michigan really diverted a lot of attention, a lot of resources to focus on Hoosick Falls. And I think, like I said, there is a direct line from that real catalyst event, that catalyst site, to where we are today in a conference, all sorts of industry, toxicology, just, that seed of Hoosick Falls has really germinated into what we're seeing today. Okay, I just wanted to put a little, historical context out there and talk about, not just the global impacts, but the real human, direct human impacts that we're feeling here with this. So now I'm going to jump into the science itself and the chemicals. And here we have, I just want to show, we have groups of compounds. These are what we can now, the specific PFAS analytes that we can quantify. We certainly know there are thousands of them out there, but this is generally the list of what we can actually measure in nanograms per liter. And we have precursors, carboxylates, and sulfonates. And the takeaway I want you to have from this slide is that's a long list. And it is. It's a long list. And that is definitely a challenge for us, this very long list. We have many more compounds, compared to TCE, PCE, or BTEX. We have a long list of compounds that we need to track and evaluate, and certainly a big challenge of that, and definitely in light of what Zeke and Chris were talking about, is communicating the risks to that. So there's a whole host of challenges there, but like I said earlier, I'm an environmental engineer. I like to use tools, and from my perspective, I also see this long list as an opportunity for us to do better site assessments and to refine our conceptual site models. Like I said, these PFAS data sets can be very large, much larger than we've been used to. And crucially, what that means is now we have more variables to look at. Variables, we can calculate more ratios. We can look at a lot more relationships than we've been able to do before in the past with these data sets, and develop more lines of evidence, especially when it comes to fate and transport and conceptual site models than we've been able to do in the past. And these large data sets are an opportunity because they open the door to more rigorous forensics, which is what I'm going to talk about for the rest of the talk here, is the idea of a PFAS fingerprint. And I think fingerprint is actually a really good term here. Here I've got a little icon of one. It's a visual shape that is a unique ID to a particular thing, whether it be our thumb, or with PFAS, it's that unique ID of a source. So what about PFAS chemistry lets us do this fingerprinting? And in my mind, there are two critical factors here. The one on the right, there are many analytes. Like I said, there are lots of variables that we can scrutinize, evaluate, develop associations with, so a lot more lines of evidence. But the left-hand side, the fact that these are forever chemicals also helps us develop a fingerprint. And by that I mean that PFOS, PFHXS, the perfluorinated compounds, they are not degrading under ambient conditions. So the PFOA molecule you see up gradient, once it migrates down, it's still going to be the same PFOA molecule. So these are conservative tracers that we can use in the environment. And a ratio of one chemical to another, it empirically works, and from a fate standpoint, since they are virtually indestructible and not degrading in the environment, that we can use that to our advantage here for PFAS fingerprints. Let me go into a quick case study here on a landfill that I worked on. You can see this is a 3D representation of the topography there. You can see the landfill mound, and it actually has pretty cool solar system built on it right now. This was a big quarry that the town decided to fill in with garbage without lining the landfill. And in fact, on the bottom right of your screen, which is downhill, there are a number of unfortunately placed residential supply wells. Thus, the impetus and the hurry for characterizing this site right here. Like I mentioned, there is no liner. There was a cover put on it. The methane still being detected, so the waste is still decomposing, and the leachate system really isn't doing that great a job. So I think with a lot of our sites were still in early days. For regulatory reasons, for a whole host of reasons, and that's true at this site. So here we've used just the monitoring wells that were installed to monitor the landfill itself to conduct a PFAS assessment. And you can see the sample locations, got monitoring wells. Also have a handful of surface water locations as well around here. And so what I want to do for the rest of the presentation is talk about 3 different conceptual site model questions and talk about how fingerprinting can help us elucidate the conceptual site model for PFAS contamination sites. The first one I want to talk about is, what can it tell us about quote-unquote background PFAS? Secondly, the groundwater to surface water pathway, so the discharge of contaminated groundwater to surface water and to contaminate groundwater. What can we figure out with fingerprints there? And lastly, I'm going to talk about vertical migration. But starting, I mentioned earlier, I had the icon of a fingerprint saying, we really want, at least for me, because I really like to see visualized data, I want to see a picture that is the PFAS fingerprint. And here we have a pie chart. I honestly think this is just a visual circus that is almost impossible to comprehend in pie charts here. So there's got to be a better way, and I know Zeke had one in his presentation, and I saw them earlier, and there is a better way. It's the radar plot. These are also called radial plots. They're also called spider plots. The good news is that you can pick this from your Excel charts list and easily generate this. So let's unpack what we're seeing right here. A radar plot gives you multiple axes, not just, X and Y. And here, what we're doing is, in one sample, plotting the concentration of these constituents on that axis. So I wish my laser pointer worked, but it doesn't seem to be working. So for example, we have PFOA there at about 13, PFOS, what is that, about 27 nanograms per liter. There are many, many different ways to develop radar plots, and you can iterate until it starts making sense. But here I've summed up the other carboxylates, summed up the sulfonates, and then summed up the quantified precursors, which you can see is a big non-detect here. So what I really like about this is that now we have a shape, right? We can compare shapes, squares to squares. I was thinking this morning that, my daughter is in preschool right now. She's probably working on shapes too, So we learned about comparing shapes very early on, and it works and it's handy. So moving on with radar plots. The first one, background PFAS. And you can see that one of these plots does not really look like the other. And that really is the whole point. And the actually fairly simple point here is that if we have a way to visualize the data that's in an easily readable shape, these sort of oddballs are gonna jump off the page. And I've seen this really at site after site recently, that when we visualize with radar plots, the one who's not like the others really just jumps right off the page. And so here, we can see shapes that do look very similar. No, it's not perfect, but it's really from a conceptual site model perspective of where we are, and given all the uncertainties of site assessment, this is really good, to be that close and to have it visualized right there. So, here we are with background PFAS. The next question, groundwater to surface water pathway. To answer this question, we broke out our toys. And here we have one of the drones from our CDM Smith drone squadron. And the red arrow right there is pointing towards the thermal imaging camera. So we took this out to our site, and the thermal imaging camera views the world in temperature. So the bar there on the y-axis is actually temperature, from very cold to whitish is warmer. And this was a very cold day. This is not in Florida, by the way, you may have guessed it. A lot colder there. Yeah, right. This is a very cold day, and was a snapshot from the drone, and you can see our pilot there saying, "Oh, I see something over there," and this is. You can see the whiteness right where he's pointing to, and that is the thermal signature of warmer groundwater that has now discharged to surface water. And that was the whole point of the thermal imaging with the drone, was to fly around and identify these thermal anomalies. And with the drone, we can do it on a broad scale. We can do it rapidly. And find the surface water hits to sample. Now the cylinder, white cylinder there is the leachate collection sump, and you remember I talked earlier about, well, it's not quite doing its job. You can see the effects right here. So I think of all our fingerprinting, this was the one that almost got me the most excited, because as we saw the monitoring wells earlier that had a very similar shape, comparing a surface water fingerprint to the surrounding groundwater, it wasn't like, oh, we found some PFAS, maybe it came from somewhere else. No, those shapes are virtually identical. And so this is one more just really strong line of evidence here of the groundwater to surface water pathway. And maybe here, it was everything sort of lined up, but my hope here is that these are some tools that you can take back to your sites and think about. And here we had a very successful example of documenting, for the purposes of CSM, that groundwater to surface water pathway. The last one I want to talk about here is vertical migration, and on the right-hand side we actually had, this is the MW6 cluster, which had a S shallow, a deep, and then X does not mean extreme depth, but maybe it could, the very deep well. And again, it's what doesn't look like its neighbors is really, I think, a valuable exercise for interpreting the PFAS data, because it opens, it opens a door for you to say, this requires further investigation, or there's a separate source. And again, the reason this works is because of the conservative nature of these PFAS forever compounds. The ratios, at least empirically, and the data I'm seeing downgradient, these ratios do not change dramatically. I mean, somebody here is going to say, yeah, Chris, what about precursors? And that's a good point, and I'd love to talk to you about your experience with precursors to see, if you've dramatically seen ratios change. Thus far, in my experience, I haven't seen them change all that much, which, that's a whole other topic of conversation, I think. But empirically, the radar plots are given a lot of value and they're actually pretty easy to develop in Excel. And that's where I want to end it now, is where to with forensics. Well, maybe simple is not the right term, but a more straightforward approach of radar plots is really given a lot of value, and I've seen this on a number of sites now for getting to at least elucidating the big components of your conceptual site model. There are, more advanced techniques that are out there, and certainly a lot are coming. There's linear versus branched. There's suspect data evaluation. There's multivariate statistics. My hunch is going to be that the majority of sites aren't really going to need those to get to the point of where you want to go, developing remedial, having enough knowledge of your site assessment, develop remedial alternatives. But of course, there will be instances out there where multivariate statistics and suspect analysis will be the linchpin for everything. With that, thank you very much for listening.
Well, that was a good one. Wasn't expecting that. Chris Gurr, Ziqi, and me, if there are any questions that we could answer for you, we'd be happy to do that. And just pick your poison. Yes, ma'am.
I noticed that the list that anybody used. Oh, thank
Here you go. Thank you.
Hi, I wanted to know, are you just using 537.1 in the sample sets for toxicology, or is anybody using 533? The lists are different, and,
Sure.
and that's why.
Yeah, I've seen both, but 537 is more common, I think, from what I'm
Okay.
seeing.
Okay, so
that-
most of the stuff is using 537.1 for the drinking water. And you have seen studies done with 533?
Right, but not many.
Not many?
Yeah.
Okay, maybe I'll ask you
Okay.
if,
Or I can send you
copies of that.
something.
Thank you.
Yeah, sure. Does anybody here have an experience in that, want to answer that question?
No, but I was going to ask another question.
Okay, fair enough.
I've got a couple, but let me start with Chris. So you seem to be sort of discounting differential transport of all these things. You know, you're sort of looking at this like they're bromide, and you've got bromide and chloride, and they sort of move together. But, you know, from what I see on the transport, and that's both air-water interface transport, transport through soils, and transport with distance, these ratios are going to change with time. So I didn't quite see your shapes as correlating as well as you did. So I'm sort of curious how you account for that, or whether you're accounting for that when you're sort of doing this type of analysis.
I know which Chris that's directed to.
Is there two Chris's? I'm sorry. I'll call you Doctor and Chris. How's that?
Yeah, thanks, Paul. In my mind, this is really an empirical exercise. I mean, conceptual site model, I totally hear what you're saying, you know, differential transport. At least what I've been seeing so far is, and I was looking at data yesterday, is, you know, a lot when you're looking at source differentiation, the shapes are just so different, you know. There's probably a lot you could do to tease out, and if you really wanted a detailed model, perhaps a numerical model, to put in those type of, you know, differential transport factors like you're saying. But and certainly that's something people can take on and tackle. But, you know, I think in my experience, and I really don't do a lot of numerical models because, you know, we get to the conceptual site model rather than the really detailed transport model answers the mail for the majority of my sites is what it seems like. So what I'm noticing is that from just an empirical looking at the data, the shapes, yeah, they may tweak around the edges, but there's almost a remarkable consistency down gradient. And I'm curious if you have different experience and see it differently. I'd love to hear about it.
Yeah, I don't. I just, you know, when you say those shapes are so similar, maybe I pick up differences because of my nature, but
yeah,
I wouldn't want to sit in a court and say all these shapes are the same, you know.
Yeah.
Because, you know, with the parameters you're looking at, I don't know that they're close enough, or, you know, other things. I mean, people mention precursors. You're not measuring many precursors with that method. You're measuring 3 or 4, right? And so maybe 96% of what's there is precursors that could be transforming. I mean, you know, I understand your principle, but, you know, it's
right.
I think there's a lot more. There's an awful lot more that's going to have to go into this to sort of understand that, you know, those changes over time or distance.
Yeah, and I can certainly, I mean, if you're in litigation in that type of setting, I can certainly understand how that'd be something important.
Great, thank you.
It's going to be really challenging to do any analytical or numerical, you know, feed transport modeling. Let's say just for one compound, PFOA, you know, the retardation factor by itself, it can be 5 to 10 times different. You know, the KOC value reported or studied by different research groups, can be from 300 to like an EP value 2,500. So it's going to be challenging.
Another question?
Dr. Teaf, given the ubiquitous nature of these compounds and the extremely low levels that are very difficult to measure, I noticed in the studies that there are unexposed controls. Do you think there really are any unexposed controls in human or animal populations?
Thanks for the worst question I've ever heard from you. You're exactly right, and that's always an issue with controls, is making sure, and it's particularly a problem with human populations now, because we don't know if anybody really is not exposed at all. Mm-hmm. In the animal studies, you can have geographical separation, which you think will do enough to do that, but it's always a question. The controls and how good or how well they represent a non-exposed population is always an issue.
And then this is a polling question. My understanding is in 2023, which is only next year, the public water systems are going to have to be measured or analyzed for certain of these compounds. I'd like to see what the panel thought about what's the percentage of public drinking water sources which will fail on those parameters that are measured.
Gentlemen, I think it's a big number.
Yes.
Go ahead. Go ahead.
Yeah, I think that, the UTMI 5 data is going to show larger fraction of, our public drinking water system with more PFAS detected compared to you.
He doesn't care. He cares, but he doesn't want to contribute. That's a good question. And in any kind of a circumstance like that, you have to be careful that you, what you wish for, because you might get it. And when you start analyzing large water supplies, the sources of which sometimes you know, but maybe they're blended sources, and then you have to go back and figure out which one of the wells of the 6 or 8 is contributing. It can really complicate the issue. Can I get in a couple more questions if there are some?
Sure.
Yes, sir.
This is for Dr. Teaf. I just had a quick question about, in terms of what we know now, and there's maybe not enough, but in terms of the large number of PFAS, is there a subclass in terms of what their innate properties are? Is there a subclass that we're more worried about in terms of the acids versus the sulfonates versus the alcohols? Is there one that stands out as the higher risk group, if you will?
I'm not there yet. I don't think you can say that categorically. We may be able to, but we, having a couple of hundred out of 10 or 15 or 20,000, I don't know that we know that. We could be badly surprised later. But that's the kind of information that if it stood out, it may clarify some of the uncertainties I'm talking about. If you found one group that you really cared about, it might make a lot of the rest of it irrelevant. You're exactly right. Yes, sir.
Yeah, I really don't have a question, but I just wanted to follow up on. So we're starting to see a lot more 533 and 537 requests together, where the 533 handles the majority of the compound list, and then the 537 will do the additional 4 that are not on the 533 list. So we're starting to see both requests. So you're going to probably see more data from the 533 method. And we're also starting to see requests on the new method, the 1633 that's coming out, which has 40 some odd compounds on it. So you're 6 months, a year, 2 years from starting to see that data.
What I was getting at is that 6.2 FTS, so what I'm getting at is that 6.2 FTS, I've seen it a few times, but it's not an analyte that's on 537.1. So you'll see in a lot of your remediation 6.2 FTS, but it's not on the 537.1.
Yeah.
So just wondering, are people running both lists, and that's what they're asking for?
They're starting to. UCMR 5 has the list of compounds that they're looking for, and it's a combination of 533 and 537.1. Where
Well, yeah.
Let me ask you
they're
this, are
different.
people doing that because they really want to know both, or they just know there's two methods and they want to just see how they match up?
That's a good question. I really don't know the answer. I think they're looking for the entire list in the drinking water parameters, and they're not getting it from either method.
Right.
So they're saying, okay, well, we can do 533, which has isotope dilution and so on and so forth, and get the bigger list, and then we'll just supplement it with 537.1. They're not asking for a redundancy in compounds, you know, where the lists match. They're just looking for the 4 that are not on the 533.
Right.
So, yeah, it's just been an interesting dynamic that way.
Well, and in a much less complicated way, we had the same problem for years trying to evaluate chromium, where people would say, well, you know, my total chromium numbers are this. We'll assume it's all hexavalent chromium. And then they would look at the toxicology, and it's probably not all hexavalent chromium, but if you assume that it is, your criteria are way low. And so that may turn out to be a problem where the analytical chemists in the room have to help us decide what's the best way to approach characterization for a given site or a different water supply. It may differ.
Yeah, I just had one quick comment. You know, when we talk about how widespread this is, I mean, I think we all have to keep perspective on the concentrations we're measuring. You know, if you start looking for a part per trillion of benzene or mercury or lead, it's going to be in all the water supplies too. So I think there's sort of this, you know, sometimes I find this hysteria, but if our detection limit for these compounds was a few parts per billion, the perceived issue would be far less. Granted, I understand the toxicological part of it, but every time I hear the forever chemical and it's everywhere, you know, to my knowledge, in drinking water systems that have been tested to date, 1,4-dioxane is far more prevalent than PFAS at the current concentrations that they're measuring. So, you know, I think there's a little perspective in my mind that we have to be careful about, you know, the concentrations of things. And when we get to a part per quadrillion, we can measure a lot of other contaminants at that. You know, metals are the true forever chemicals, right? We're not changing metals anywhere. You know, so that's just a comment. And one other thing was, I looked at your blood data, which was really interesting, but there are studies that predate that too, aren't there, that show, so your data on blood levels of PFOA and PFOS, I'm aware of some studies that go back maybe 10 years before that again showed even a 60% decline between like 2000 and 2006. So that suggests that, you know, we've had a very strong decline in these over a decade, or say almost 2 decades now. What do you attribute that to? I mean, what was that source that was removed? It certainly is not drinking water, because we've done very little to our drinking water supplies. Is it food packaging? I mean, do you have some thoughts about those declines in blood?
I know. I think that's a real question, because if you look at something that goes...
Chris, can you cover that?
Yeah.
So we can pick this up.
Anytime you see something like that, 2011 to 2018, and you see a decline, you want to know what happened before that. And if you see an even bigger decline before that, is it an analytical question? Is it a real decline? Or have you removed a source without even knowing it from the exposure pool? I don't know the answer to that right now.
There's an ES&T study that was a blood supply. So it was people who donated blood in 2000,
Yeah.
and then they sampled them again in 2008. And it was like 14, my recollection is PFOS was like 14 and a half nanograms per liter in 2000. Wow. So there is something, it'd be interesting to take years, you know, I realize there are different studies, but to try and see sort of in general whether it's continuing
and if
to
you
come
look at
down.
the methods, and the methods are comparable, you might be able to join those databases. I'm not sure.
Yeah.
But it's a great question.
Thank you.
I answer questions like that every single day, like everybody in this room does. What if Spartacus had a Piper Cub? I don't know.
All right, I think this is going to be the last question, and then we're going to break for lunch.
Dr. Teaf, real quick, when do you think PFAS is going to become a reportable like lead?
Reportable under TSCA
Reportable by state,
in the state of Florida?
in states across the country. Like, pardon me, when do you think this is going to be like a mandated reportable thing that laboratories and everywhere are going to have to start putting this data out there?
1, 10, or 100 years, I'll say 10. 1, 5, or 10, I'll say 5. I would be surprised if the analytical precision and breadth of the analytical techniques out there aren't becoming sufficiently well reproducible that it's going to be reportable. What you do with the data is an entirely different question, though. If it's reportable, then I have to do something with it. And I'm not sure, well, I am sure that many states are not prepared for that. And you never want to ask a question that you don't know the answer to, as the lawyers in this room will tell you.
100% I agree.
Okay. Thanks very much. I think, Gene, we'll close it down.
We're at lunch, so we've got a buffet in the exhibit hall, and I got a buffet just outside the door. So
thanks very much for coming.
Separate everybody. Thank you.
Recording stopped.